the rest of these notes, we're going to get into exponential growth and decay models, kind of some application problems. So we have this formula, A of t is equal to A times, parentheses 1 plus or minus R, all to the power of t, where A stands for the final amount, capital A stands for the final amount, lowercase a stands for the initial amount, R is going to be the rate, always in decimal form, and t is time in years. This piece of the model, the 1 plus or minus R, is the growth. It's called the growth or decay factor. So let's talk about which one looks like what. When it's a growth, that's when I'm adding a rate. When it's a decay, I'll be subtracting the rate because it's negative. These models, these application problems, I find particularly interesting because you can apply them to so many things in the real world. So when you're talking about like population growth, that's an exponential growth, whether you're talking about animals or humans. If you're talking about like bacteria growth, right, that's an exponential model. If you're talking about how much a dollar is worth, that's an exponential decay, right? As we go on in life, things are more expensive, which means that our money is worth less. If you think about like the depreciation of a car over time, that's an exponential decay model, right? So once you drive it off the lot, you lose a whole bunch of money because it's no longer a new car. And as time goes on, you lose an increasing amount of money. So really kind of some cool opportunities to look at exponential decay and growth. Before we get after an example that has to do with money, let's just talk about identifying parts of these models. So example 2, determine whether the function represents exponential growth or decay. Write the base in terms of the rate of growth or decay. Identify R and interpret the rate of growth or decay. So we're just going to kind of pick apart the pieces. You may find a calculator helpful for this. Reminder that if you have your device open, you're still trying to do the Pearson Realize thing, to make sure you get that done, because I've got to assign this assignment before you leave today. Okay, great. So we've got all this information up here. All right. Basically, what's going to happen is 1 plus r is an exponential growth and 1 minus r is an exponential decay, which means that if it's a number bigger than 1, it's a growth. If it's smaller than 1, then it's a decay. So if I look at this example in here, 1/5, that's going to be a decay. It doesn't ask me why, but I'm going to write it because it's a good thing to have. Because that value of b is less than 1, it's a decay. So first part, determine whether the function represents exponential growth or decay. Boom, decay. Good, got it. The next part is to write the base, b, in terms of growth or decay. We just said that this was decay, so it's going to be 1 minus r. So I get to make a choice. If it's growth, I'm going to use 1 plus r. If it's decay, I'm going to use 1 minus r. Right now, it's somebody's paper and record it, or it will be after this recording goes up. You have to. That means you have to rewatch the video. So whatever's inside these parentheses, that is b. So this is 1/5 is equal to 1 minus r. Find r. You can find r by either moving r to the left-hand side and then subtracting the 1/5, or you could move the 1 over and then take the opposite. Doesn't really matter. So if I add r and I subtract 1/5, I get r is equal to 1 minus 1/5 leaves me with 4/5. So this part of the direction says, write the base in terms of rate of growth or decay. That's this. Identify r. R is 4/5. Then it says to interpret the rate of growth or decay. So we already said this was decay. Change this into a percentage. So if you need a calculator to do that, 4 divided by 5. I just turned that off. Gives me 80%. If this is an exponential decay, then that's an 80% decrease. It's a decay. What's my rate of decay? 4/5. How do I change that into a percentage? Just divide on a calculator. Since it's decay, that means it's a decrease. It's going down 80% every time. Do it again, same process, just working through identifying. F of x is equal to 10 times, parentheses, 2.2 to the power of x. Identify whether this is an exponential growth or decay. 2.2 is greater than 1. That means it's an exponential growth. If I were to write the base in terms of the growth or decay, I get b is equal to, this is growth, so instead of 1 minus r, I'm going to have 1 plus r. I get to make that selection. Like, oh, it's growth, so it's going to be positive, which is what we wrote over here. Growth, positive. So b is what's given in parentheses, the 2.2. And I'm asked to find r. Subtract 1 from both sides, and I get r is equal to 1.2. That's written as a rate, as a decimal. I want to change it into a percentage. It's already in decimal form, so to get a percent, I'm just going to move the decimal place over twice. So 120%. Since it's a growth, we're talking 120% increase. That's it for the identifying. We're not actually going to do this example, but I just wanted to show you this is the same type of problem. It's just what it looks like online because it has like drop down menus and stuff, but it's the same type of problem. Same exact directions. It gives you this. This doesn't have parentheses, but it's the same thing. The function represents exponential. You get to pick whether it's growth or decay. Rewriting the base in terms of the growth or decay results in the function, right? So what goes here? 2.9. In this function, find r, just like we did here. So we would write 2.9, and then if it's an exponential growth, I would subtract 1, which indicates the value of y increases or decreases by some percentage each time. So if it was this problem, it increases by 120% each time. So it's the same. Just wanted to show you the structure. That's what it'll look like online. And this will be our last example. A car is purchased for $24,000. Find an exponential model if it depreciates by 20% each year. Now find its value after 7 years. those emails were coming through that you were hearing ding annoyingly, we're just saying that the Wi-Fi is spotty. It's working for some and not for others. So just a heads up. So the first part of this problem that we get to do is we get to actually write the model, which just means write the equation and fill in all the information. So I know that these models look like A of t is equal to the initial amount times 1 plus or minus r all to the power of t. And I'm using t. The computer might ask you to use x instead as the input. That's okay. They're the same. When it says find an exponential model, that just means find an equation. If it says the word depreciates, right, that clues me in that it's a decay. And I've got a percentage, but I need to turn that into a rate. So here, I don't want to plug in 1 minus 20. I need to change the 20% into a rate. So I move my decimal place over twice, and I get 0.2 for the rate. Little a is going to be my initial amount. That's the initial amount that the car cost, so $24,000. To find the value that goes in the parentheses, I can either use 1 plus r if it's a growth or 1 minus r if it's a decay. This is a decay. So I'll subtract a rate of 0.2. I have a b value of 0.8 to the power of t. If I'm remembering correctly in your Savas assignment, I think they have you just use y instead of a of t. I think the answer should look like that. It'll give you a hint in the problem. So that's writing the equation. That's your model. And oftentimes that's the hardest part, right? Just organizing the information, making sense of it. And then the last step is now find its value after 7 years. So I'm just going to plug in 7 for my time. I don't want to spend the time doing that on paper in my head. So that's 0.8 to the power of 7. Order of operations says you have to do the exponents first. And then I would multiply by the 24,000. And then another little food for thought. How do I know where to round? So when we're talking about money, we're almost certainly round to the nearest cent. This is $5,033.16. Well, that's not worth very much money, but it's probably fairly accurate depending on the brand of car that you buy. If you lose 20% of a $24,000 car, that means in the first year you lost $4,800. And then you lose 20% of the existing cost each year after that, after 7 years. Might be worth about $5,000. It's probably not too far off, depending on the brand. Some brands, some makes keep their value longer. Okay. Any questions on that problem? All right, then that will finish us up for 5-1.